Okay, so one of another application of differentiation is actually rates of change. And to really understand what rate of change is, I think the best way to do this over an online platform is to show your compare two different shapes, and which is will be a cup, right? One in a cylindrical form and one in a cone form. So let's look at the cylindrical form. So imagine if I pour a water, okay, and then let's assume that the rate at which I pour the water in, it's constant. Right? It means it's flowing at a constant rate. So if I can split it into 12 different, let me say I split it into 12 different, or let's say equal intervals, equal height. Okay, so over here, let's kind of like split it into equal height. Okay, I don't know whether I'm doing this correctly. But 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, okay, whatever. Okay, but it should be 11. But can I say that at every instance of this, right? If let's say they are equal height, let's say all these are like, let's say 1.5 cm, 1.5 cm, right? All these are 1.5 cm. Can I say that the water amount at every 1.5 cm is actually the same, right? The amount of water that flows into to fill up that 1.5 cm of depth is actually going to be the same. And we can actually kind of like record the speed at which not speed lah, the rate at which the depth increases over time, and it takes 16 seconds, right? And it kind of like it will be a linear constant line. Okay, it will actually, yeah, the water will flow linearly, right? Because it fills up the height at a very equal amount, right? At a constant amount. However, if you look at a cone, right? Let's say I fill up 1.5 cm, okay, over here. So let me just duplicate this over here, make it smaller. Okay, so assuming that I fill up 1.5 cm of this cone, right? This is what the 1.5 cm will look like, right? And then I fill up another 1.5 cm. So which is over here. We're going to expand it out to here. And so the difference here is that will the amount of water in the first part be lesser than the amount of water be in the second part? Okay, and then let's think about it. Let's say I fill up another 1.5. Right? So assuming I fill up another 1.5 over here, will this amount now be larger? Right? In some sense, we can say that the water is filling up at a kind of like exponential rate, in some form lah. Right? It could possibly look like, and you fill up like much faster, right? So it takes shorter time to fill up that first 1.5 cm. Takes a little bit longer to fill up the second 1.5 cm. A bit more at 1.5 cm. Why does it take shorter time at the start? Because the space is very small. So water flows faster inside, right? It's faster to fill up that depth. Then once it goes up to the second one, right, it takes a little bit longer. And then if it goes to the third 1.5, it takes a little bit longer than the previous part. So in the sense, the graph at which the height increases over time for a cone will be vastly different from the cylinder. It will look something like a curve over here. Okay, I may not be doing it right, but yeah, you get the idea. Okay, let me just position it well. Okay, it will look like that. Okay, no, maybe more like that, I guess. Okay, and why? Because really at the time will be, it will take a little bit longer time to fill up the top part, right? So imagine once you reach a certain level around here, the last 1.5 cm will actually 1.5 cm of depth will actually will take longer to fill up that. Okay, so we can say that the gradient of the cylinder is in fact linear, while the gradient of the cone is not linear anymore, right? But how do we actually find the gradient of at which? So what we want to understand here is that since it takes 16 seconds, we know that it takes 16 seconds to fill up the cone cup. Okay, and we know the volume of the cone cup, which is 240 cm cubed. We say that the rate at which the average rate it's actually 15 cm cubed per second. How do you get 15 cm cubed? You take 240 cm cubed divided by 16 seconds, right? So since the height of the conical cup, right, is 12 cm, the depth of water in the cup increases from 0 to 12 cm in 16 seconds. So we know that about the volume. So what about the average rate of change in the depth of water? Right, the depth of water is definitely not rising at a constant rate in the cone cup. Okay, so as I said earlier, we assume that the flow of water is constant and the water is to be dispensed at a certain constant rate of 15 cm cubed per second. We want to talk about the instantaneous rate of change of the depth of water at a particular time. Okay, why do we say instantaneous? Because it's a little bit hard for us to, like, if let's say I pour something from, so I start now, I pour for 15 seconds, right? Honestly, can I stop pouring at 7 seconds? I mean, can lah, but then it will affect the experiment, right? So we're gonna assume that we can somewhat freeze time, and let's say at a particular time between 0 to 16 seconds, maybe I can freeze time at 8 seconds, and I can figure out the gradient by drawing a tangent to the curve, or by using differentiation to find the gradient of the tangent t. Okay, so we're gonna let the tangent. Yeah, so generally, if a quantity y depends on a quantity x, we usually write it as y equals fx. However, the derivative dy over dx, we can interpret it as an instantaneous rate of change of, we usually interpret it as an instantaneous rate of change of y with respect to x. Okay, so very easily, so if this, what it means is, if I change x, right, I change a variable x, right, y will definitely change, right? And we want to figure out the rate at which it's changing, right? When I change x, how fast, how slow is y changing, right? So going to a very simple example over here, I have volume over here that is connected to x, right? Sorry, not volume, v, which is connected to x. I want to find the rate of change. When the question asks for rate of change of v with respect to x, the question is simply asking for dv over dx. Okay, so there's a little bit of interpretation game here. You need to understand what the question is asking, and you're supposed to leave your answers in terms of pi. So, firstly, differentiate. So dv over dx is simply 1/3 pi times 3x squared plus 2 pi times 2x plus 3. Resolve them, you'll be pi x squared plus 4 pi x plus 3. Now, at x equals to 2, dv dx will then simply be pi times 2 square plus 4 pi times 2 plus 3. And so you just need to simplify them, and then you will get 12 pi plus 3. Pretty straightforward, right? So therefore, rate of change of v with respect to x is 12 pi plus 3. Usually there will be some form of units, but in this case there's no units for this question. So it's a very simple application of differentiation to find the rate of change. But is it, I know the understanding can be a bit tough, but actually the doing is actually quite simple, right? So yeah, that's all.